In this lecture, I want to discuss recursive solutions to the state space formulation. So as we mentioned in the previous lecture, the state space formulation for a linear dynamical system looks like this. X dot equals AX plus B P of T. Again, from the previous lecture, we know that the solution to this first order differential equation looks like this, right? And again, X is the state vector, which is, in the case of structural dynamics, displacement and velocities. So this is a linear set of differential equations that we're solving. And in this equation, X naught is the state at t equals to 0, and P of tau is the loading, and tau is the integration variable, and t is the time at which we want the state. So we begin with X naught, and using this formula we can move directly to X at t by multiplying that initial state by e to the at and integrating the input from 0 to t using this convolution integral. Now what we want is a recursive form. We want a recursive form that basically, if we start at X of t, we can move to X at t plus delta t. And that we would like that to be in some kind of form where we multiply the state at X, t, we multiply a matrix times that, and we multiply a matrix times some kind of function of the load between t and t plus delta t. So the first step to doing that is to simply think of this as if we are solving for just a single time step. So if you think that we are at t and we want to move to t plus delta t, I'm showing in this diagram right here. Imagine this is some kind of state. I mean, it's a multidimensional problem, but I'm just solving here in 1D so we can visualize it easier. So you want to move from t to t plus delta t, so you can think of tau as going from 0 to delta t, right? Just a relative time. And if that's the case, then the first term of the equation is simply e to the a delta t times x of t, because x of t is like at 0, right? In our new relative time. And the time step is delta t, and then the integral becomes this expression that we're showing right here, which goes from 0 to delta t, because we just want to solve for one time step. Again, here notice that instead of t, I have delta t, because I'm not going from 0 to t, I'm going from 0 to delta t. So this first part is easy. This integral is a little more challenging, and I'm going to solve it here. So again, we're going from 0 to delta t, and we have the integral. The first step is to discretize or simplify the behavior of P of tau. So how does the input behave from 0 to delta t? The simplest way to do that is to use what is known as the zero order hold. That basically assumes that the load is constant between 0 and delta t in tau, which basically means that the load retains the same value that it had at the beginning of the step. So you take the value of the load at the beginning of the step and just continue that on for the whole duration of a single time step. If the time step is small, that's probably a decent approximation, and let's see what comes out of that. So if P of tau is now constant, equal to P of t, meaning the value of the load at the beginning of the step, then we can take that P of t out of the integral. Then we are left with this integral right here. To solve. And if we do a change of variables, so we're going to define a new variable z equals to delta t minus tau. If we take the derivative, we arrive at this expression here. D tau is equal to minus dz, and so that will substitute in here. And if we look at the limits, substitute the limits, when tau equals to 0, z is equal to delta t, and when tau equals to delta t, z equals to 0. So our new integral, which in this case, we go from 0 to delta t in tau, our new integral is minus integral delta t to 0 e to the az dz, and the b, because it doesn't depend on z, goes out. If we use the integration theorem that says that you can flip the limits of an integral if you change the sign, then this integral here becomes this integral right here. Flip the limits, change the sign, and then using standard vector calculus integration rules, we obtain this result right here, which if we evaluate in the limits, we obtain the final result that we seek. And so writing the whole thing again, we see that the state at t plus delta t equals to e to the a delta t times x at t plus a to the minus 1 parentheses e to the a delta t minus the identity parentheses times b times p of t. So this matrix here, e to the a delta t, becomes our matrix F that we were seeking here at the beginning of our discussion. And this whole matrix here becomes our matrix G that we were talking about at the start of our discussion. And this whole function here of P between T and delta T plus delta T is simply P of T, the value of the load at the beginning of the step. If we write this in terms of time steps, then we obtain this really simple and nice recursion that x at k plus 1 equals f times x at k plus g times p at k. And so you can move in this form recursively, right? Whatever you get here, you just put it back in here for the next step, and you look at the value of the load at the beginning of the step and continue to move on and on. Couple of